frontier, which looks for deviations in the naturally occurring events in our universe, and it mostly looks for dark matter particles among others. And Xenon 1-ton are cast are examples of such experiments which probe different parameter regions of dark matter particles. Then, of course, there is LHC, which looks for direct production. It probes around GeV to TeV scale with order 1 coupling. But today's talk will be mostly based on this intensity frontier. And I reiterate that intensity frontier is where one uses intense source of beam, very high luminosity, and looks for rare processes in the standard model. And the experiment that I'll focus on today is BEL, and which looks for rare B decays mainly. And the particle that I'll talk about, as I said in the introduction, axion. Now, axion is important for several reasons. First of all, it solves many drawbacks of the standard model, namely strong CP problem, which I'll talk about in detail. It is a fine-tuning problem of the standard model. In some benchmarks, axion can be an excellent dark matter candidate, and it can also play an important role in the baryon asymmetry of the universe. So my focus will be on this experiment and on axion, which typically solves all of this. Now, axions have acquired much attention in the recent past, and this is a plot to show the citations when the first Pechequin paper came out in 1977. And as you can see in the recent past, the citations have gone up exponentially, showing that it is a nice place to work on at present. Okay, so this is the brief outline of my talk. I'll first introduce what the strong CP problem is and how axion solves the strong CP problem. For typical axions, the axion mass and the pion masses are related by the relation Ma Fa is equivalent to M pi F pi, where Fa is the decay constant of the axion. And when Fa is very large, around 10 to the power 10, 10 to the power 12 GeV, axion can also act as a dark matter candidate.
May I ask a question?
Yes.
Yes. You spoke about the QCD axion, which comes from this Pechequin symmetrical for QCD. But in general, what you are saying, there are many kinds of scenarios which lead to axions. So do your specific conclusions depend on the QCD axion assumption, or are they applicable to general axion scenarios?
So the whole work would be dedicated to an axion which only talks to GG dual.
Okay.
But
fine.
in the course of this talk, when I show the constraints and the results, I will show that if axion couples to other particles such as quarks or even photons, how sensitive the bounds can be. This I'll mention in the talk. But in the first part, at least, I'll only focus on GG12 because it has direct relevance with the strong CP problem.
Okay. I'm asking this because there are scenarios where the axion arises from the spontaneous breakdown of some other U1, but the axion can, leptons in principle can possess some axion kind of Pechequin charge in that sense. So axion may couple to a pair of leptons. So I'm curious about whether your studies will include such scenarios as well.
So yes, so two of the famous UV models which generates axion, one would be KSVC, one is DFSC. DFSC where the Higgs are charged under the Pechequin symmetry, and therefore, as you say, axion can talks to leptons because Higgs talks to leptons. In this talk, at the very end, I'll talk about some of them, but primarily the focus would be an axion which only talks to GG dual. So if you have some UV theory in mind, you can consider the KSVZ model where the axion talks to GG dual only. Is that okay?
I understand. So maybe when you discuss your results, you can come back and kind of mention or rather explain to us whether how much of this is valid if you go beyond the QCD axion scenario.
Yes.
So we'll wait for you for that. Oh, thanks.
Okay. Okay, so at the beginning, as I said, I'll talk about strong CP problem and how axions solve it. However, the axion suffers. Axions were there is a noise in the background. Probably okay. So yeah, so the typical axion where the axion could be a dark matter candidate is where Fa is 10 to the power 10, 10 to the power 12 GeV. However, that also induces a problem which is known as the axion quality problem. And therefore, heavy QCD axion is well motivated as it can solve or ameliorate the axion quality problem. I'll talk about what axion quality problem is. After this brief introduction, I'll also talk about what are the present day searches at the intensity frontier, how one looks for axion in pion-kaon decays, beam dump experiment, neutrino experiments, and so on. But all of this, as you can imagine, pions have mass around 150 MeV, kaon around 500 MeV. So all of this would constrain an axion which is light. Now, if one talks about a slightly heavier axion, then B decays are an excellent probe, rare B decays. And I'll talk about some of the technical challenges and subtleties of such a calculation. And then I'll talk about our results and some future directions. So let me first begin by saying that the...
Sorry, Sabyasachi, may I ask a question?
Yeah. Sure.
Since there are many persons in the audience who are specialists in other areas, can you just explain for everyone's sake what is meant by a beam dump experiment? Because you use that terminology. Many people may not be familiar with the term. It will be very helpful if you will do it.
So this is just the outline. I have a separate slide for beam dump experiment. Now in a single word, beam dump is where you get rid of the sources for neutrinos. So a typical intensity frontier on neutrino experiment is where you hit a high energetic proton beam into a target. The target produces a plethora of mesons, pion, kaons, and they decay to neutrinos. But a beam dump experiment is where all those neutrino sources can be isolated. So I'll talk about how beam dump neutrino experiments can be used as a beam dump experiment. Okay. So first the introduction. The standard model Lagrangian can be extended with a term GG dual with a coefficient theta. This term is parity violating because the dual there is epsilon tensor and therefore CP violating. Now interestingly, this term can be written as a total derivative, and we know this total derivative reduces to a surface integral which vanishes at the boundary. But this is only true for perturbative field configurations. For QCD and for instanton-like effects, this total derivative is non-zero, and therefore CP is violated at the non-perturbative level. But this is only one source of strong CP. There could be other sources. For example, the Yukawas, the quark mass matrices in general are complex. Now you can rotate away this complex phase by doing a chiral rotation on the quark fields. But as it turns out, under chiral rotation, the measure of the action is not invariant, and it picks up a term which is proportional to GG dual. So there are two sources. First, as I said, you can extend the standard model with the GG dual term. And secondly, because of rotating away this phase by using a chiral rotation, you generate a term which is proportional to GG dual. Therefore, there are two contributions of the coefficient GG dual. And this is, as I write, as theta bar, which is the bare theta term that you extended the standard model with, and the quark mass matrices.
Sabyasachi, can I interrupt you here? So this GG dual is what? This is what is this? This is the field, the gravitational thing, metric.
This is the gluon, the gluon field strength.
This is gluon field. I see.
Gluon field, yeah.
Okay. So this is and this is a third rank tensor.
Yeah.
And this is the tensor.
So these are the color indices, and this is mu nu as the Lorentz indices. So A goes from 1 to 8, and mu nu is the Lorentz.
So A is, I should think of A as some internal degree of freedom, and mu nu's are related to the spatial and temporal degree of freedom.
It's actually a second rank tensor. Second rank Lorentz tensor.
That's what I realized. With 3 indices, I was thinking it's a third rank, but under Lorentz transformation,
that's why I said
this
is the color, and this is mu nu as the right.
Thanks.
So the
parameter A shown in is not a continuous parameter. It has discrete values. 8 possible values, like 8 colors in a blue one. 1 to 8.
This is SU3, is it?
This is SU3. Yes, you can have similar terms for WW dual and BB dual. It turns out BB dual is not physical. You can completely rotate away, but you can have a WW dual term as well. But the basic
theta is defined modulo something, is it? The theta parameter. I think it breaks. You said it breaks parity symmetry.
Because there is epsilon tensor here over here.
Right. And does it automatically means that due to CPT theorem it breaks CP also? Sorry, C and P also?
Yes, it breaks parity, therefore it breaks CP. And that would mean it breaks time invariance.
Yeah, it does. So it does break time invariance.
Yeah, that's right.
But is there a special value of theta for which it does not break time reversal symmetry?
So it would be 0 and 2 pi, and because those are the minima of the potential.
What about pi? What about pi?
So it has a cosine-like potential. QCD induces a cosine-like potential, and the minimas are. So if you can wait, I'll show the potential once I show the structure, and then we can talk about this. So it has a shift symmetry associated to it. So 2 pi f. So theta goes from theta plus 2 pi alpha.
Okay, I think at pi you again restore time reversal, and then there will be an interesting question to ask: what happens to your system?
Okay.
Yeah. Okay. Fine.
Okay. So there are essentially 2 contributions. One, you extended the standard model with, one from the quark mass matrices. And this I write as theta bar, which is the sum of these 2 terms. So theta bar, again, sum of theta and the term coming out from quark mass matrices. And one would naively assume from just order of magnitude estimation that this would be order 1. But if this is order 1, it can have major consequences. For example, it would generate very large neutron electric dipole moment via this diagram. And from experiments we have observed, the neutron dipole moment is very tiny. I mean, we have not observed it. Experiments have given us limits on the neutral ADM. Now, when one calculates this diagram, it turns out that theta bar, which is the coefficient of this term, has to be less than 10 to the power minus 10 to satisfy the constraints from experiments. And this is the source of some strong CP problem, that a term which otherwise would have been order 1 is less than such a small number. So this has to be fine-tuned. The 2 contributions need to be fine-tuned to fit this very small value. This problem was famously solved using axions, where again, it used to be theta bar, but theta bar is now promoted by a dynamical field axion, and Fa is the decay constant. Now, if one is interested about how this term comes out, and as this was asked in the beginning, one can consider a model like KSVZ, where this Lagrangian has a U1 symmetry, Pechequin symmetry, and P is a complex scalar field. Now, when the P gets a wave, the axion becomes the pseudo-Goldstone boson of the theory, and it talks to the heavy quarks. So if you replace the P with the wave and the axion, and it talks to A, QL bar, QR. So these are heavy quarks. Now again, just in the beginning, as I said, you can rotate away any phase by doing a chiral rotation. Therefore, you can also rotate away this phase using a chiral rotation on these heavy quarks. But again, under chiral rotation, the measure of the action is not invariant, and this picks up a GG dual term. So that is how one can think of how GG dual term arises. But for the time being, let us just use the fact that the theta bar coefficient has been changed to a dynamical field axion over a length scale, which is the decay constant. Now, just as I said in the beginning, you can do a chiral rotation again to rotate away the GG dual term, but then you pick up different terms. So if I rotate away this GG dual by doing a chiral rotation on the quark field, I generate a derivative coupling of axion and quarks, and also the mass matrix changes. Because this is a chiral rotation, QL transforms differently, QR transforms differently, and MQ hat is essentially related to the chiral rotation and the quark mass matrices. So these in the literature are commonly known as two bases. People either work in this basis where you have AGG dual, or they can work in this basis where you rotate away AGG dual by doing a chiral rotation, but you then have derivative coupling of axion with quarks, and you have mass mixing of axions. The usefulness of such a rotation is as follows. If one rotates away the AGG dual term and have only axion quark couplings, then it can be matched with an effective theory of mesons or baryons, and we have such an effective theory, which is the chiral Lagrangian. So therefore, the usefulness of this for this rotation helps us to match this theory with an effective theory of chiral Lagrangian. And the most important term in this context is in fact an isospin breaking term, where this MQ hat is same as the curly M, sorry for the difference in notation, and it contains the axions, and the sigma are the meson matrices. So for example, sigma would be exponential I pi a ta, pi a would be the pion fields if you consider only 2 flavor scenario. If you consider 3 flavor scenario, sigma would contain pions, kaons, eta prime, and so on. So this term in the chiral Lagrangian is the source term where axion coming from MQ hat mixes with pions, and therefore all the experiments which look for in all the experiments where you have pions or kaons, you can essentially constrain axion through such a term. So I recapitulate again. I had a theta bar GG dual term. I rotate it away using a chiral rotation, but then I generate axion coupling with quarks. These couplings could be derivative coupling or mass mixing. And the usefulness of such a rotation is I can match it with an effective theory of chiral Lagrangian, where sigma contains the mesons and MQ hat contains axions. Now, after a little bit of algebraic manipulation, you can show that this term essentially generates a pion axion potential, which is of this form. And as it turns out, this potential naturally minimizes to 0. So therefore, instead of choosing theta bar to be small by doing a fine cancellation between the two terms, we now have a dynamical solution where the axion field minimizes to a CP conserving minima, which is 0. So therefore, you dynamically solve the strong CP problem. And also, since this is a simple potential, all the mass and mixing can be very trivially obtained. If we consider only 2 quark flavor scenario, you have only pions and axions. And in a 2x2 matrix, the masses are very trivially obtained, and also the mixing. And the mixing turns out to be pion mixing with fermions times this F by FA factor. So whatever pion talks to, axion also talks to with this suppression, which you can call as sine theta. As I said in the beginning, in typical models where axion could be a dark matter candidate, Fa could be very large, 10 to the power 9 to 10 to the power 13 GeV. That means this mixing angle would be extremely, extremely tiny. And there are other motivations for axions as well, such as baryogenesis.
So, Sabyasachi, again, maybe I
However,
missed,
yes,
sorry for interruption.
yes.
Maybe I missed it. When
No,
you
no,
say
it's okay.
mixing angle, what is mixing with what? These are like flavor mix.
This is a as the potential shows. If you consider only two flavor, two quark up and down quark scenarios, so this is a 2x2 matrix containing pions and axions. The eigenvalues one would give the pion mass, the other would give the axion mass, which is related to the pion mass. And the mixing essentially comes from the off diagonal, which is something like f pi over fa.
In essence, can I say this, that as a function of time, an axion eigenstate will go into a pion eigenstate and vice versa? They will keep on. You have matrix element between pion states and axion state. Is that correct? That's what the potential is.
That's right. That's
so if
right.
I start off like a pion, after a while I can become like an axion. If I look at the magic time or the time period, whatever the time period is.
Something like oscillation, you mean?
Yes, yes. But that's what it should mean, right? Because it's a 2x2 matrix. After all, it's a two-level system, and what you're saying is there is a magnetic field in the two-level system, and if you start with a non-eigenstate, it will have, spinning of
There
this
would be
eigenstate
mixing
around.
from the other.
Yes. That's what it sounds like. Is that what it is?
Right. Yeah. Essentially, yeah, the same thing.
And when you're saying mixing is small, now what should I think? The pion to the axion conversion will take enormous time. Is that what you're saying?
Exactly.
That is what.
Yeah. Exactly.
And what kind of time scale you have in mind? What is the typical time scale?
So let's say f pi is around 150 MeV and fa is typically around this huge scale, 10 to the power 9 to 10 to the power 13 GeV. So you can imagine this suppression would be huge, 10 to the power minus 9, minus 10 suppression.
So at the present time, if you are an pion, then it will never see it's converting into an axion practically, you are saying, because it's just too long.
Right. Yeah.
So, but still, I mean, in compared to what time scale it's long, can you tell us? I mean, like, is it like the Big Bang time or what? I mean, what kind of time scale should I? You're saying it's large, but compared to what?
I am not sure about the time.
Maybe if it is not on top of your head, we can go ahead. Maybe you.
Yeah. Okay. Yeah. At this point, I'm not sure about.
Because I think experiments. That is what if they are a short time scale, probably then which are within the experimental time scale, then of course we expect to see it. Otherwise, we don't. So that's why I think I'm asking.
I mean, there are specific experiments which probe some specific regime. For example, pions talk to photons, axion also talks to photons, and there is a oscillation because axion talks to two photons, for example, let's say, and you can replace the one photon with a magnetic field. And using this, one uses certain experiments such as light shining through wall and so on and so forth, where axion converts to a photon, and there is this oscillation. So under such
so you're basically saying that axion photon conversion is very much faster, and that might be very much probed.
Yes.
But this one might be tricky. This one might be tricky.
Exactly. So there are dedicated experiments only for those, but they are in a different region which I would focus on. But essentially, people talk about that. These are light shining through walls sort of experiments.
Thank you.
Okay. So. As I said, axion would solve the strong CP problem, and additional motivation would be it can be a dark matter candidate, but when FA is very large, 10 to the power 10, 10 to the power 11 GeV. But such a benchmark, although you get dark matter, but you lose a very important thing, which is as follows, and this is the source of strong CP problem. The QCD induced potential, or the structure of the potential which I showed, was m pi square f pi square roughly, which you can say as lambda QCD to the power 4. So the QCD induced potential is so shallow that any higher dimensional operator which breaks this U1 symmetry can shift the minima away from the 0, which is the CP conserving minima, therefore jeopardizing the whole strong CP solution of the problem. And just to give a numbers about this, for example, gravity is supposed to break this U1 Pechequin. And if I just from naive dimensional argument, if I write down that gravity breaks U1 Pechequin suppressed by Planck scale, from dimensional argument, I would put the decay constant over here, so Fa to the power 5, and lambda should be order 1. So this is a higher dimensional term, which should be less than the tree level potential that I wrote down, m pi square f pi square or lambda QCD to the power 4. Now, if I just plug in some numbers for Fa, let's say 10 to the power 5 GeV here, lambda turns out to be less than 10 to the power minus 10. As I said, for dark matter, Fa would be much higher, 10 to the power 10 GeV, then lambda would be an extremely tiny number. So it would imply that I have shifted the whole fine-tuning argument of why theta bar is less than 10 power minus 10 to something like why lambda is extremely small. Therefore, this is the basics of the quality problem, and therefore it would make sense if Fa is around a TeV scale or so. Therefore, this higher order effects, breaking of Pechequin symmetry via higher order terms can be neglected, and you still can have a strong CP solution.
But Sabyasachi,
Yes.
Sabyasachi,
Yes.
So what is this dimensional analysis? So why it has to be suppressed by M Planck only?
Yeah, so you can assume, so I assume that the Pechequin is broken by a dimensional 5 piece. Now, if you assume that higher dimensional operators such as dimension 6 or 7 would break Pechequin, then you might have a different, slightly better scenario.
Okay,
but
yes,
you have to strengthen the UV in such a way that it does not get broken by dimension 5 and gets broken by higher dimensional operators. So that again becomes a little tricky.
Okay, thanks.
Okay. So what would we like? This is the QCD line. As you can see, for QCD axion, the basic QCD axion, which is completely ruled out because of experiments, which I'll talk about now. There is a wiggle room when Fa is very large, 10 to the power 10, 10 to the power 9 GeV. There are open parameter space. One of the experiments which was asked, like light shining through walls, axion photon conversion experiments work in this region, but this is problematic from axion quality problem. So what we will focus on are lines which schematically passes through this, opens up. So there are two motivation, opens the parameter space is completely open, and you also ameliorate the quality problem. However, in order to do so, you need to break this relationship. And a lot of work in the recent past, model building works in the recent past have gone in this direction, where such a mass relation can be violated. In this talk, I will not talk about those papers, and there are quite a few. But what I will mainly focus is, let's say you have an axion which talks to GG dual, which solves the strong CP problem. Fa is around a TeV scale, therefore also ameliorates the quality problem. And how would we look for it? So this is the basics of the work. But just before going into the details of our work, I'll just briefly talk about how such constraints come about. One example is yes.
So therefore, with this high mass QCD action, so you are giving up this dark matter possibility, or is it still on?
I am, yeah, that's right. I am giving up the dark matter possibility in the common sense, but I mean, to solve dark matter, either you want to have more actions in the theory or more structure. So some model building is required. But you are completely right that I am giving up the dark matter. So I gain some, but I lose some as well.
Okay.
And another motivation is since we have dedicated experiments now looking for this, so it's a good idea to have something to say about this region. Okay, so one of the bounds come from pion decays, for example, and these are old experiments, but which people considered very recently. So as I said in the beginning, if pion talks to leptons or quarks, any fermions, axion would also talk to them, but with a suppression. And now what people did with pion processes were, for example, pi beta experiments where charged pion decays to pi naught electron neutrino. This is phase space suppressed, therefore branching is extremely small. Or pi nu experiment where pi plus decays to electron neutrino. This is suppressed because of chirality, and the branching is around 10 power minus 4. Now, if you have such a decay where pi plus goes to a pion electron neutrino, then pion axion mixes. So at the final state, you will have axion electron neutrino. Now, if axion decays to 2 photons, you will have a similar signature such as this. If axion is long-lived, you will have a similar signature such as that one. Therefore, you can use these experiments to probe the axion parameter space. But as you can see, the bounds on the mixing angle is not that great. It's around 10 to the power minus 4 minus 5, which can be translated to a bound on Fa, because sine theta is 10 power minus 4, 5, minus 2 or whatever. And it turns out that Fa can only be constrained up to a few GeV, so which is not that great. Kaon experiments, on the other hand, are a little more helpful. The idea is essentially the same. Kaon decays to a pion and axion. If axion or K long decays to a pi naught and axion, if axion is long-lived, then K plus would have a similar signature which is observed in Na62. If axion is long-lived in K long decay, then it would have a similar signature which is probed in Koto experiments. Again, the branchings are extremely small, which helps to constrain the parameter space, and you get around hundreds of GeV in the bound. So this is from pion and kaon decays, but please notice that in every cases the mass, you cannot extend the mass up to over a few hundred MeV because of the constraints on kaon mass and pion mass. Beam dump experiment, as I said in the beginning, that beam dump essentially takes away all the sources for neutrinos, and the argument is the same. You have a high energetic proton beam which hits the target. It produces a plethora of mesons, pions, kaons. Again, pions and axion mixes. Pion goes to an axion might decay to 2 photons or something else, and you can observe Cherenkov rings or other things in the detector. And using the standard background, one can constrain the decay constant and the mass of the axions in quite a significant way.
Excuse me, but the pion can itself be a source of neutrinos. So what is the mechanism whereby the sources of neutrinos are removed?
Neutral pion, you take away the charged pion. You take away all the charged pions. So you are only here with the neutral pions.
Okay. So what is it? Is it some strong electric field or strong magnetic field?
Exactly.
Diverting
strong magnetic field which diverts all the charged pions. Yes. In some cases, you can also put up a shield which absorbs most of the charged pions. But yeah, that's the basic argument.
Okay. But won't they decay even before they are diverted away? I mean, so how do you really avoid them decaying while they have a significant component of their velocity along the beam axis?
So I'm not, at this point, I'm not sure at what's the magnitude or at what point they are, but certainly before they decay, they are diverted. The numbers I don't have, but they take it very seriously. I mean, they do it very efficiently. That okay. I can tell you.
Okay,
so,
that's enough. I mean,
minibone, microbone, everything can be used as a beam dump.
Yeah. Okay, thank you.
Okay. Okay, so all this combined, you get this wiggly line, which gives you constraint from pion decays and kaon decays, mostly from intensity frontier. This is the QCD line, as I talked about. It is completely excluded over here, but there is open parameter space when Fa is large, but then again, you have the axion quality problem. There are also constraints from astrophysics, but those are for axions which are light around a keV or so. Most of the constraints come from stellar cooling. For example, take for example sun. Sun has a core temperature of keV, so axion can be produced, but the mass has to be around a keV or so. So that's why the stellar cooling constraints are at low mass regime, and we have an empty region around it. Now, as you remember, all these the constraint from pion kaon decays relied on the mixing between axion and pions, and which we deduced using chiral Lagrangian. We rotated away the GG dual turn, axion coupled to quarks, and then it was matched with chiral Lagrangian, and therefore all the pions axion mixings were obtained using chiral Lagrangian. But the problem is when you talk about few hundred MeV to few GeV, B2S transition is one of the best example. And the moment I talked about QCD axion and B2S transition, it is clear to you that it becomes a two-loop process. So it's technically challenging. And another thing is you cannot use chiral Lagrangian anymore, because next to leading order terms in chiral Lagrangian come up with this suppression delta over lambda. The lambda is the cutoff scale in chiral Lagrangian, which is around a 1 GeV. And if you are proving few GeV axion, then delta over lambda is a large number. So your power counting becomes, breaks down. So therefore one has to do a perturbative calculation, and this is what I'll talk about in the next few slides. So again, you start with this minimal consideration that axion only couples to GG dual, therefore solves strong CP problem, and there is some additional mass of the axion from some dark sector or some other sector, which helps you to deviate the axion mass from the pion mass. And the process that we are looking is B decays. At the quark level, it would be B2S transition via this operator, and this is the famous penguin diagram. But please remember, axion talks to GG dual, therefore it has to be a two loop. One loop would be from the W and the top quark, which changes the flavor, and the second loop is the gluon loop, where axion is attached. Now the whole methodology is start with this, and you have to match it with the effective operator. Essentially, one has to calculate the Wilson coefficient because of this matching. But that's not enough. I mean, we also need to know what else gets generated, what are the other operators gets generated because of operator mixing, and what are the effects of the RG equations as well. So very briefly, these are the main four diagrams which we considered. So W again changes the flavor from B to S. It's a rare process. And on top of that, you have this gluon loop where axion is attached. The gluon loop can be here, over here, over here, or over here. So there are essentially four diagrams. The important part is, because this is two loop, you have a double pole, you have a single pole, and a finite turn. Now these double poles or these poles can be both UV poles. We generate UV poles when the momenta diverges. This can be also infrared poles. The infrared poles can come because you have light quark propagators here. You have light quark propagators here. And when the momenta of these light quarks vanishes, you can also generate a IR pole. Now therefore this epsilon square can have contributions from both UV pole as well as IR. And it is very important to distinguish these two effects, because ultimately my effective theory can have IR divergences, but all the UV divergences should cancel out. Therefore, I need to separate out the UV and IR poles, and this we do by adding a fictitious mass in the light quark propagators. As I said, IR poles come from light quark propagators. Therefore, by adding a fictitious mass, you can separate out the UV and the IR poles. So the basic structure is, you had all the two loop diagrams. There are double poles, there are single poles, finite term. In order to renormalize the theory, you need to know what are the counter terms. The counter terms come from shrinking either the gluon loop, which is a subdivergent diagram, or shrinking the W loop, which is also divergent. Shrinking the gluon loop, shrinking the W loop is of course there in the standard model, but shrinking the gluon loop generates axion quark-quark coupling. As you can see, if you shrink the gluon loop here, the axion line gets attached to the quark line, and indeed you generate axion quark-quark coupling. When we added the counter term, we noticed that the 1 over epsilon square term completely goes away. But still, we are left with 1 over epsilon term, and this overall 1 over epsilon pole can be, we need to also get rid of this using a counter term, which comes from the axion of diagonal quark couplings. So the take-home message is, two loop diagrams have 1 over epsilon square pole and 1 over epsilon poles, and the counter terms you need at the UV are axion quark-quark diagonal coupling and axion quarks of diagonal coupling. With the help of these two operators, you get rid of all the divergences. Therefore, it means you need axion quark-quark diagonal and off diagonal couplings at the UV itself. Remember, we started with AGG dual coupling only. But to make sense of the theory, to get rid of all the divergences, we need axion quark-quark and axion of diagonal quark couplings. This cannot be changed. So we need the three operators altogether. So this is one part of the question which was asked at the beginning. So am I only considering axion GG dual? And what I'm trying to convince here is I cannot have only AGG dual. I need axion quark couplings diagonal and off diagonal to make sense of the theory, to get rid of the divergences. Therefore, the structure is, even if I start with GG dual, I need all the three operators. Of course, these operators come with their UV coefficients. You can choose it by having a specific UV model.
So Sabyasachi,
yes.
Sorry, I mean, I could not quite follow it thoroughly. So, are you saying that the QCD? So, you are saying that QCD to renormalize it, you have to have you have to have some more operators in the theory itself. Is it the statement?
That's right. Yes, that is the statement. In order to get rid of the divergences, you need to have axion quark couplings as well.
And that statement is applicable only for the GG dual term, not for the G square. I mean, what is special about? Because I thought, when you say it's a renormalizable, I mean, that means the theory is, we don't need any more beyond the theory, correct? I mean, to add these extra UV operators.
No, but we need, see, this is axion over FA, so it's already dimension 5. Axion GG dual is dimension 5 over FA. So this is a non-renormalizable term which is generated at the scale FA. So therefore you need more structures to make sense of it.
Okay, so
did I?
Okay, no, sorry. Let me think. Let me think. I mean, I'm sorry. I mean, maybe I should think. Okay, please go ahead.
I mean, this is what you generate at the scale FA from some UV model.
Can I interrupt you once? Yeah. So what does it mean? I mean, if your axion can couple to the quarks, what does it mean for matter in general? I mean, the atoms, the way we think, the protons, the neutrons. I mean, how should I think about them? I mean, you think that the axion can be inside it, but that cannot happen. I mean, I'm not a particle physicist. I'm just curious.
It means axion would couple to it, but whether or not you have any significant, whether or not you have any significant effect from observation depends on what scale is it, and for that you need to look at deviations from the expected results. So, for example, I can give you an example. If axion couples to quarks, then in neutron stars or in supernova, you will have axions emitting from quarks. There would be processes where
a quark gluon plasma, then only you can see it. You really, if I think an isolated stable proton, I mean, then I should not be worrying about axions and this kind of coupling of quarks with axions. Is that what you're saying? You need a plasma to see it?
Why would I need a plasma? I did not
No,
understand.
but that's because that is where I started. I mean, if you have a stable proton, now what you're saying is the axion can couple to the quarks. So now, do I worry about the stability of the proton itself, for example?
Yeah, so all it depends on the scale.
Of course, now if you go
in
to very
most,
high energies where you have broken the
yeah,
protons into the plasma, then I understand they are bare running around, and then there is a different
right,
aspect to the problem.
right,
So that's why I'm asking this
right.
question. What does it
So,
mean
so I would
to
say
have such a
any
term?
observation. So any observational difference depends on the suppression scale. If the suppression scale is too large, you might, in most cases, not see any observational effect.
I see. You mean at the level of just stable?
And neutrons, I should not worry about the.
Right.
What about the plasma?
Yes. Yes.
Neutron star, as
Exactly.
you said, that if there's a plasma, then I should worry about it. Is that what you're saying? That is where one should look for it, and why?
I said because neutron star, it's a very dense object.
Right. It means there's a plasma form
And
probably inside it, right?
there is
That's
a
what you have.
plasma and axion would couple to it. So what happens in things like that is when the axion comes out of the star, it could be a white dwarf, it could be a red giant or a neutron star. It takes away energy, which essentially means the star cools at a faster rate. So using the stellar cooling observation, you can constrain the scale again.
I see.
This is what I meant from the observational point of view. So because axion couples to quarks, using stellar cooling constraints, you can effectively constrain the scale.
Oh, thank you.
Okay, but yeah, as you know, I mean, for that we need some specific ranges of axion mass, because axion also needs to be produced. If it is too heavy, the temperature of the star might not be sufficient for an effective process.
And such a coupling is by definition gauge invariant, is it?
Yes.
By construction.
Yes, by construction.
Okay.
So yeah, as I was saying, even if you start with GG dual, you need other operators just to make sense of the theory, just to get rid of the divergences, essentially because this is, you started with a dimension 5, which is suppressed by the scale. Then next part for our case is trivial. You run it down to the W mass scale where you have this operator, you match it with the Wilson coefficient. The Wilson coefficient will have contributions from all three operators. CBS is contribution from this one, CQQ is the contribution from that one, and C3 is the contribution from this one. Now, once you have the Wilson coefficient, you can run it down again to the bottom mass scale where the B physics experiments are running. And that's how we can probe what the scale is. So this is the anomalous dimension matrix, which takes into account all these diagrams. So what we noticed is the main contribution comes from the off-diagonal axion quark coupling, and it drives the Wilson coefficient. So the major contributing factor to the Wilson coefficient is when the axion couples to the off-diagonal. Others interfere destructively, but their contribution is smaller. So if I recap before quickly, so how much time do I have? 5-7 minutes, something like that?
Yeah, yes, definitely 5 minutes for sure. I mean, it's
okay. Okay. So far what we have done is, again, I recapitulate again. I start with AGG dual, but I see that I need other operators as well. For example, axion, quark, diagonal, and off-diagonal couplings. They come with their different coefficients, but you can have a UV model where those coefficients are large, or you can have a model where there's a small. In our context, we considered them to be small, but if you have a different UV model, those coefficients can be very large, axion quark or axion off diagonal. Now, when you have all the three operators, you run them down using RG evolution. You match it at the W scale where you get the Wilson coefficient CW. You can again run it down to the bottom mass scale where the experiments are running, and then use the experimental numbers to constrain what the effective scale is. To go into the details of, before going into the details of the experiments, we would like to do a back of the envelope calculation. And as we see in Bell, the number of signal events over the background depends on many things. It depends on how many pairs of BB bar are produced at Bell. At Bell is around 10 to the power 6. At Bell 2, it would be around 10 to the power 8, if I'm not mistaken. Branching B to Ka, this was our calculation. At the quark level, it's B quark going to S quark and axion. At the meson level, it's B meson going to K and axion. This was only about production. The axion also needs to decay. And if you have a similar coupling, the axion would mostly decay to hadronic modes. As this was asked in the very beginning, you can have a different model where axions can also go to leptonic modes, but then the production might also change and you might get completely different phenomenology out of it. Then there are efficiency factors. These are basically cuts and so on, and some order 1 isospin numbers. So if you so as you see, I have two plots where I choose the UV scale to be either 1 TeV or 10 TeV. That means I run it from 1 dV to the W mass scale or from 10 TeV to the W mass scale. And the branching that I get is around 10 to the power minus 6. Let's say if this is 10 to the power minus 6, as I said, the number of BB pairs are around 10 to the power 8. So this is 10 power minus 6. This could be 0.1, this could be 0.1. So you would get an order 1 signal event. So naively, it means that using this branching fraction of 10 power minus 6, you can already constrain hundreds of GeVs or like a TeV from the experiments. And that's what we did. Axions are produced from B decays at Bell, which is a E plus E minus machine, which generates upsilon at the resonance. Upsilon readily decays to 2 Bs and then B goes to an axion. So this is how Bs are produced at Bell. Then B goes to an axion. This was our calculation. Axion then decays to a lot of hadronic modes because you only have GG dual, so it will only decay to hadronic modes. We took the branching fraction from this paper, and then we computed what could be the efficiency factors and isospin factors. Now I'll not go into the detail of every experiments because of time constraint, but this is the basic plot which I want to show. This is for lambda is 1 TeV and this is for 10 TeV. That means you start the running either from 1 TeV or 10 TeV. If you run it from 10 TeV, you get large logarithmic correction. Therefore, the bounds are more stronger. These are different decay modes, axion going to eta pi pi or axion going to kk pi or axion going to phi phi. And then we also have projections for Bell 2. And as you can see, we can almost rule out 2 TeV, or for the lambda UV 10 TeV scale, we can also rule out much more parameter space. So all these under this curve will be ruled out. And this is Bell 2, which will have results in a few years. B2SA is an inclusive process at the quark level, and that is already comparable with all the light meson bounds that I showed from pion decays or kaon decays. Another distinctive feature of these two diagrams is the following. You see 3 lines for each constraint. These 3 lines come because you have 3 different operators: AGT dual, axion, quark, diagonal, and off diagonal. If you vary the Wilson coefficients within the allowed range, this gives you a maximum, minimum, and a central point. But when you go to a higher scale, the large logarithmic corrections dominate, and the UV values are sort of become insensitive. That's why these lines are close together. But roughly, this is the picture. Now, for this plot, we only considered axion to prompt decays. Axion can have displaced vertices also. If the
Sabyasachi,
yes, yeah.
sorry, if you So if I understand this plot, so what is the statement? The statement is that BEL2 is going to see all the way up to this green dotted lines.
That's right. If BEL2 finds any deviation from the standard background, then one explanation could be an axion, and then the axion decay constant would be around this range.
Okay, and those different different colors are the predictions that is coming out from the models.
So these different colors are predictions which from our calculation, and different colors essentially mean different decay modes of the axion,
Okay.
different processes of the axion.
Okay,
So
thank you.
Yeah, so this is all about prompt. Axion can have displaced vertices as well, because the lifetime of the axion might be a little large, so that it does not decay readily at the primary vertex. So it will be produced, it traverses a little bit and then decays. And if that is the case, then we computed the efficiencies for such a process, and such new regions can be probed again using axion displaced vertices. So this is, I think my 1 hour is over, and this is the conclusion of the talk, that if you have AGG dual, even though it is a two-loop process, but BEL2 experiment can really probe a vast part of the parameter space. We showed that if you even start with AGG dual, you will need more operators just to make sense of the theory. And then by doing a RG evolution and matching it at the W scale, we get strong constraints. When the mass of the axion is around the GeV, you can get strong constraints on FA, which would be few hundred to 1 TeV. We considered many decay modes for the axions. Some other extension can also be thought of. As was asked, if axion talks to leptons, then of course axion can go to leptons, but the production process might not be two loop, it could be one loop as well from B decays. And some of those works have already been done in the literature, but I am sure there are empty spaces where one can work on. Axion can have other different Weizumino interactions, Weizumino-Witten interactions also, and it can lead to some interesting astrophysical implications, such as cooling of stellar objects and bounds from that. There are other directions of axions as well, but in a different parameter space, different mass. One which I worked on recently was something like a kinetic misalignment, which can explain dark matter and baryogenesis together, solving the strong CP problem. But it has also the axion quality problem. It has a problem from axion quality. So it's hard to explain everything satisfying the quality issue. So yeah, this is, I'll end my talk today. So this is what I wanted to say, that axions are pretty interesting. A lot of work is going on in the recent past, looking for axions at intensity frontier, that is Bell-Babar experiments, or from astrofrontier. Axions can solve strong CP as well as can be a dark matter candidate, can explain baryogenesis and so on. In this work, we concentrated on probing such an axion if it has only the GG dual coupling, and we showed that large part of the parameter space can indeed be probed using rare BDKs. So this is all. If you have more questions, I'll be happy to answer them. If I missed some questions, we can also talk about it.
Okay, thank you, Sabyasachi. So please.
Thank you.
Thank you. So anyone wants to raise hands?
I have a question.
Yes,
Can I go ahead?
Please.
Yeah. So I understood that you started with a initial Lagrangian. So maybe can you go back to that slide where you introduced the Lagrangian? Then you did a gauge transformation probably to gauge away those last two terms, right? Yeah. And then you had the. Right. So and then later on, what you told us is that you need to the theory to be renormalizable, you need to add some more couplings to this, where there's a direct coupling between the quark fields and the. So now, how
Right.
does it impact your, as far as the CP violation and so on is concerned? Initially, you started with this argument that this introducing this term, which I was asking, basically breaks time reversal symmetry. Then, of course,
but
through
these
CPT
are,
theorem,
yeah,
Now,
these are at the same footing.
they are the same footing. How does one see
Yeah,
that?
they are at the same, because
And-
if you only have a GG dual term, if I forget about the axion is a complex part of a complex field. It's a pseudo Goldstone boson, right? So G dual has the epsilon tensor, and therefore GG dual term itself violates parity. Axion also violates parity, and therefore this total term is invariant under CP. Okay. Now, when I have axion quark-quark couplings, the
Which means it's
situation
also
again is the
invariant
same.
under T. The total term is
Right.
invariant under
The
T.
total term is invariant under T, but not the GG dual. When you include
By
the
itself,
axion, it
exactly.
becomes invariant. Right.
Yes.
Now, here also you have a gamma 5 and an axion, which sort of
I see. Okay.
makes it invariant. Here also you have a gamma 5 and an axion.
So does
So
this,
these
as
three
you,
terms.
so I think, is it
Yeah.
is this something you are trying to preserve a symmetry? That's why these are the terms which are appearing, or you can have, as you do RG in principle, I would imagine that there's nothing which tells you that you have to preserve. CPT theorem, of course, have to be sacred. But then,
Right.
is it necessary that the symmetries which you started with, they have to be there? I mean, probably not, right? You can have spontaneously a term generated which break the symmetry. So
Probably, let me think. Even if I start with, let's say for the timing we forget about the dual, and let's say if I have AGG which breaks it, would I generate something which preserves ultimately CPT? I do not think so. I mean, at no point I introduced any breaking effect. So RG, I am not sure if RG would generate any weird terms.
in a sense, unless you constrain your RG with the same set of symmetries, why should it?
Yes, exactly. Yeah, that's the answer, right? So when I don't have a coupling which either protects or violates that, RG would not generate such a term by itself.
So you are not allowing for the way the
Yes.
procedure
Yeah.
has been worked out. You are not allowing
Right.
for any such thing. I see.
Right. Yes.
But can it be there in principle? Phenomenologically, can one introduce or not? Or it's ruled out?
Phenomenology. I mean, I have to have a breaking, a coupling which violates this. I have to introduce something. Then you can generate a whole lot of other operators. But there has to be a coupling which breaks this. It's of course would not be a standard model coupling, but you might need something else.
Okay. The other question is, the way you introduced the counter term was by shrinking this thing into a point, right? Which basically
Yes.
means
Yes.
you are going, I should say, lower in energy, right? I mean, in a sense, I'm losing resolution of this process. So I'm going lower in energy, that I'm running towards the infrared. Is that correct? So is it true? I'm trying to understand, you see, the way you introduce the counter term, it
So
involves,
okay. So by shrinking what? So
kind
yeah,
of losing some resolution of a process, and that is when effectively you said the quark is directly interacting with the the axion. So again, this question of scales, when is this relevant? When is this coupling?
Good. So for example, probably this could be an answer. Please let me know if this answers your question.
No, sure,
As I said,
I'm just curious.
this is a two loop. So you have UV poles as well as IR poles, right?
Right.
Now the UV poles would come when the momentum diverges, and the IR poles comes because you have light quark here, and light quark momenta can go to 0. That will give you an IR pole. What I meant by shrinking is this sub diagram itself is UV divergent. So when I shrink this, that means I am actually generating an axion quark-quark coupling where the gluon is at one loop. That's what I meant by shrinking. But you generate this axion quark-quark just to tame the UV divergence that comes from this sub diagram. That's what
That doesn't it mean that effectively I should not think of the gluon anymore because I don't see it anymore? In a sense, replacing a propagator by some kind of a number, right? I mean, then that's
Right.
kind of at that scale, it is no more a propagator. Like we study weak interaction, we if you don't zoom in, then you don't see the structure, and you can replace it by an effective
by
mass one over
effective 4
m minus
Fermi, yeah,
right?
4 Fermi term, yes.
4 Fermi term. It is something like that.
Yeah.
Now, at
Similar
what
to,
scale? Yeah, exactly. So now my question is, what energy scale should I associate it with? So then only I will know when the direct axion, this thing, axion quark coupling is relevant for me, right? Right.
Yes.
Exactly like in the weak interaction, we know when it is 4 Fermi like and when it is not. It's a question of scales. In a similar, it's very much in a similar spirit. You can answer this question. I'm just curious, and maybe there's an answer to this question.
It has to be above the top and the W. That's for sure.
Okay.
So,
yeah, does anyone want to say?
Would you like to take any other questions if there are anything? I mean, otherwise we can continue with this.
No, fine. I think I'm pretty much done. We can have.
No, I have
after
not
the
thought
talk,
about it in that way. Yeah, but yeah, that's an interesting way to think about it. I don't have the answer right now, but yeah.
Fine.
So
okay.
one is of course this is a derivative coupling and it picks up. So by using equation of motion, it picks up a mass and effectively it would be mass over Fa.
Absolutely.
So Fa would be the driving scale which would be important. So Fa cannot be lower than the W or the top mass, but essentially more than that. That's what naively I think could be the answer.
Yeah.
But
fine.
it's not exact.
Yeah,
by any means.
thanks.
Yeah.
Yeah, okay. I think others might be having questions.
Anyone else has any comments or questions? Okay, I'm not hearing anything. So Sabyasachi, I had a quick one. So should I understand that the mass range that you are talking about, this heavy QCD axion, is not probable by any astrophysical or cosmological probes? Is it the broad statement?
That's a broad statement. So for example, if you look at sun has a core temperature around a keV. So that means it can only through Primakov or through other processes can produce axion, which will be at around the same mass keV. So if I go to supernova, it can produce a little heavier axions, few hundred MeVs. Probably, I'm not sure about the exact numbers, but certainly much heavier than sun. But supernova, we know there are fewer far between and the constraints are not so much. But effectively, this would be the statement that astrophysical observations are most effective for light axions.
Okay.
Around the keV to MeV-ish region.
Okay. And you also said at the beginning that you're thinking this is not playing any structure formations issues, so that also kind of drops this cosmological issue. You said at some point.
I said what?
No. You said that it is not doing anything for the dark matter. This heavy.
This heavy one cannot be a dark matter because, as you can see, what our basic idea was producing axion through two loop, and then axion has to decay. Now, if axion decays in the experiments, of course, it cannot be a dark matter. So, yeah, in that context, it might not be a.
Okay.
It might not have any impact from that. Yes.
Okay. Yeah. Thanks, Sabyasachi.
Kushi, can I ask a quick question?
Yes, please, Ghulam.
Sorry, I think Sabyasachi, I was a bit late to get in, but I mean, so you're saying that even a supernova cannot prove your thing, right? Then, I mean, what would be like probable situation where you would like to test your model?
Yeah, so for this, I would just go at the beginning. And as I said, these are the three main frontier experimental frontiers which cover the landscape of new physics. So this is very schematic, so one should not take this as a sacrosanct, but stellar cooling or other stuff comes in the cosmic frontier, which probes light couplings but very light masses. So CAST, for example, looks for stellar axions. It probes around a keV of axion and very small coupling. And the talk was mostly focused on Bell, because Bell and Babar, these are B physics experiments. It produces a plethora of B meson. B can decay to axions. B has a mass of around a 5 GeV. So axion, if it is decayed from the B meson, it can be heavier. So that's why these B physics experiments can probe few hundred MeV to few GeV with moderate coupling. So intensity frontier would be the best bet to look for heavier axions, which is motivated from the quality issue.
But aren't these energy ranges already probed?
If some of them are probed, but for axion, since it becomes a two-loop process, that's why it becomes technically challenging, and that's why it has not been probed. That's why you see a white region. That's why it's empty.
But I
And
mean,
this is the
I would
reason
like to
we focused.
look at other devil's point, advocate's point. Right? Why do I do something if I cannot probe? I mean, I'm just trying to ask you a provocative question.
But we did probe, right? We did use the experiments which are running right now and which would run in the near future. We showed that.
So you're saying that
using
it
the
is
present
not yet out.
experiments, yes, using the present experiments, you can fill up. So I should have a picture where in the broader perspective, we should have shown what the exclusion is. But essentially this region can be probed, which was not done because of technical issues or some other things.
But is there any reason to believe that it could be there?
Well, the main motivation is experiments are running, so why shouldn't we look at it? That's how I see it. I mean, the other motivation
No,
is
but there may be some physical motivation, right? Also, so.
The physical motivation would be strong CP problem, and you are solving the axion quality problem. But then again, there is experiments, so we should try to look at every place. That's my motivation, is at least.
Okay. So, Kaushik, maybe you can ask other questions like teaching and something.
Okay, thank you, Sabyasachi. So I'm just, is there anything else? Otherwise, we'll close it. It's already 4:20, 1 hour 20 minutes. So as I'm not hearing anything more, so Sabyasachi, thank you very much for being with us. So please stop by to IISER Kolkata whenever you visit next time in India. So you just came here, I just heard. So please stop by next time. Okay.
Okay. Sure.
Okay.
Thank
you very much.
Thank you for your time. Yeah.
Okay. So maybe some secretary or someone from the department will get you back with some logistical things. Okay.
Okay. Sure.
Okay. Thank you so much. Appreciate. Bye. Bye, everyone.
Bye.
Bye.
Goodbye. Bye-bye.
Bye.
Thank you all.